Hey everybody, welcome back. I hope everybody's doing well. We're going to continue our discussion on L'Hopital's rule. Last time, basically, we looked at a few different examples, but they mainly focused on indeterminate forms of the form 0 over 0 and infinity over infinity. So we're going to continue our discussion today looking at other cases such as 0 times infinity, infinity minus infinity, and 0 to the power of 0, infinity to the power of 0, along with 1 to the power of infinity. Let's begin. So let us call this 1, 2, 3, 4, 5, 6, and finally 7. So we're going to look at 7 different examples. So let us look at the first case where we have a 0 over 0. So for example, we have limit as x tends to 0 of sine of 2x over x. And if we evaluate the limit at top, sine of 0 will be 0, and limit as x tends to 0 of the bottom will be 0. So this is an indeterminate form of 0 over 0. Employing L'Hopital's rule, it says take the limit as x tends to 0 of sine of 2x over x is the same as the limit as x tends to 0 of the derivative of sine of 2x all over limit as x tends to 0 of the derivative of x. So if we look at the top, limit as x tends to 0, the derivative of sine of 2x is cos 2x, and then we have to go inside and differentiate this, so that's 2 cos 2x. Likewise, the derivative on the bottom, derivative of x, is just 1. So evaluating the top, when x tends to 0, the cosine of 0 is 1, multiplied by 2, we'll have a 2 on top, and on the bottom we have 1, so our answer is 2. Let us look at the second case where we have infinity over infinity, and consider the example, the limit as x tends to infinity of 2x squared minus 2x plus 3 all over x squared plus 4x plus 4. Taking the limit on the top, that'll give us infinity, and taking the limit on the bottom as x tends to infinity, that'll also give us infinity. So this is a second case of our indeterminate form. We're going to solve this in 2 ways. Let's consider method 1. Since the top and bottom have x squared, and that's the highest power, consider dividing the top and bottom by x squared. So we have 2x squared over x squared minus 2x over x squared plus 3 over x squared. And we do the same on the bottom. Limit as x tends to infinity, x squared over x squared plus 4x over x squared plus 4 over x squared. Now let us look at the top. We have limit as x tends to infinity, 2x squared over x squared becomes 2, minus 2x over x squared will become 2 over x plus 3 over x squared. And on the bottom, we're going to get limit as x tends to infinity, x squared over x squared, that's just 1, plus 4x over x squared, that's going to be 4 over x, and then plus 4 over x squared. Rewriting it here, and continuing, we have limit as x tends to infinity, 2 will remain as is. Now, minus 2 over x, as x tends to infinity, this term will tend to 0. Similarly, 3 over x squared, as x tends to infinity, this will tend to 0. And let us look at the bottom. We have limit as x tends to infinity, 1 remains, plus 4 over x. As x tends to infinity, this becomes 0, plus 4 over x squared. As x tends to infinity, this will go to 0. So we're left with 2 over 1, or 2. Now let us look at employing L'Hopital's rule to solve this problem, which would be method number 2. LHR, L'Hopital's rule for short. Consider the problem again. Limit as x tends to infinity of 2x squared minus 2x plus 3 all over x squared plus 4x plus 4. And this led to the case of infinity over infinity. So we're going to apply L'Hopital's rule. We're going to say take the limit as x tends to infinity, differentiate the top d dx of 2x squared minus 2x plus 3, and then we take the limit as x tends to infinity, and then we differentiate the bottom, x squared plus 4x plus 4. So we get limit as x tends to infinity. Now, the derivative of 2x squared is 4x, and the derivative of minus 2x is minus 2. And the derivative of 3 is 0. So on the top, we're left with 4x minus 2. And on the bottom, we're left with limit as x tends to infinity. The derivative of x squared is 2x. The derivative of 4x is plus 4. So on the bottom, we're left with 2x plus 4. So we have limit as x tends to infinity of 4x minus 2 over the limit as x tends to infinity of 2x plus 4. Well, if we take the limit on the top as x tends to infinity, this will go to infinity. And on the bottom, as x goes to infinity, this will also go to infinity. So we still have an infinity over infinity case. So let us apply L'Hopital's rule again. Limit as x tends to infinity, d dx of 4x minus 2 over limit as x tends to infinity of 2x plus 4. Continue, limit as x tends to infinity. Now the derivative of 4x minus 2 is just 4. And on the bottom, limit as x tends to infinity, the derivative of 2x plus 4 is simply 2. So we're left with 4 over 2, which is just 2. So same answer. Consider now the third case where we have an indeterminate form of 0 multiplied by infinity. Let us consider the example, the limit as x tends to 0 from the right side of x multiplied by ln of x. Now, since the limit as x tends to 0 from the plus of x is 0, and limit as x tends to 0 from the positive side of ln of x is minus infinity. Because remember, here's x, y, x equals 1 is here. The natural log of x will do this. And as x tends to 0, y tends to minus infinity, ln of x. And that's why we consider this limit for 0 plus or anything greater than 0, because it's not, it doesn't mean anything for negative values of x. The natural log function doesn't mean anything for negative values of x. It's not defined in this region. Now let us consider, we rewrite this as, instead of x multiplied by ln of x, we write this as the ln of x divided by 1 over x. So this is our f of x, and this is our g of x. F of x is ln x, and g of x is 1 over x. And we have the limit as x tends to 0 from the plus of ln of x is minus infinity, as we established. And the limit as x tends to 0 from the positive of 1 over x is, as x goes closer to 0, this blows up infinity. So we're going to have, in this case, a minus infinity over infinity. So that's a perfect example to use L'Hopital's rule. So let us use L'Hopital's rule to solve this problem. Limit as x tends to 0 from the plus of ln of x all over 1 over x is limit as x tends to 0 from the positive side d dx ln of x all over limit as x tends to 0 from the plus d dx of 1 over x. Continuing on the top, the derivative of ln of x is 1 over x. And on the bottom, limit as x tends to 0. Okay, what's the derivative of 1 over x? Well, 1 over x is really x to the minus 1. So d dx, using the power rule, is minus 1 x minus 2, which is minus 1 over x squared. So we have minus 1 over x squared. So continuing, we have limit as x tends to 0 from the plus 1 over x all over limit as x tends to 0 from the plus minus 1 over x squared. And this is nothing more than dividing fractions, really. So I take x squared on the top and then 1 multiplied by x. So I get limit as x tends to 0 from the plus. The x squared will go on top, and we have a minus, and the x will go on the bottom. So we have limit as x tends to 0 from the plus, and minus x squared over x is just minus x. So as x tends to 0 from the positive side, we just get 0. Now let's consider our fourth case, which is infinity minus infinity, and consider the example, the limit as x tends to 0 from the positive side or right side of the cosecant of x minus the cotangent of x. And recall that the limit as x tends to 0 from positive of the cosecant of x is really the limit as x tends to 0 of 1 over the sine of x. And the way I remember that is that the cosecant of x is 1 over sine x. It's not 1 over cos x. It's just c and s are, it's not the same. So that's the mnemonic I use. And now we have 1 over sine x. As x tends to 0, sine of 0 is 0. So this is a 1 over 0, which is an infinity case. And also now recall that the cotan of x is 1 over the tan of x, limit as x tends to 0 from the positive side. So this is limit as x tends to 0. Now, tan of x is sine x over cos x, so 1 over will be cos x over sine x. So cotan of x will be cos x over sine x. And as x tends to 0, we're going to have limit as x tends to 0 from the positive. We're going to have cosine of 0, which is 1, and sine of 0 is 0, so this will be an infinity. Therefore, we say that limit as x tends to 0 from the positive of cosecant of x minus the cotangent of x is going to be an infinity minus infinity case. So let us employ L'Hopital's rule to see what happens. So using L'Hopital's rule, we have limit as x tends to 0 from the positive of the cosecant of x minus cotangent of x is really the limit as x tends to 0 from the positive of 1 over the sine of x minus cos x over sine of x. Well, we have a common denominator of sine of x, so we can rewrite this as 1 minus cosine of x over sine of x. Now, using L'Hopital's rule, this tells us that we take the limit and we take the derivative d dx of the top, which is 1 minus cosine of x, all over limit as x tends to 0 from the positive d dx of the bottom, which is sine of x. Now taking the derivative of the top, derivative of 1 is 0, and the derivative of cos x is minus sine x, so we already have a minus, so we're going to have a plus on top, sine x, and on the bottom, the derivative, and don't forget limit as x tends to 0, and on the bottom, limit as x tends to 0. So the derivative on the bottom, the derivative of sine x, is cos x. Therefore, on the top, limit as x tends to 0 of sine x, that'll be 0. And on the bottom, limit as x tends to 0 of cos x, that's going to be 1. So our answer is 0. So you can see how we translated an indeterminate form of infinity minus infinity to a determinate form using L'Hopital's rule and arriving at a solution of 0. Let us now look at the fifth case, which is 0 to the power of 0, and consider the limit as x tends to 0 from the positive side of x to the power of 3x. And we can quickly see that if we were to apply the limit straight, we would have a 0 to the power of 0 case. Now, let us write this as let y equal x to the power of 3x. Then the natural log of y, taking the natural log at both sides, we have 3x ln of x using the natural log rules. Therefore, the limit as x tends to 0 from the plus of ln of y is really limit as x tends to 0 from the positive of 3x times ln of x. Or we can write that as limit as x tends to 0 from the positive side of the natural log of x over 1 over 3x. So those are. Now we have an f of x, which is ln of x, and we have a g of x, which is 1 over 3. Now if we take the limit as x tends to 0 from the positive of ln of x, this is going to be minus infinity, and on the bottom, the limit as x tends to 0, 1 over 3x. As x goes to 0, 1 over 0 blows up, so it's going to be infinity over infinity. So we employ L'Hopital's rule. Employing L'Hopital's rule, we have limit as x tends to 0 from the plus of the natural log of x over the limit as x tends to 0 from the plus of 1 over 3x, and we take the derivative of the top and the derivative of the bottom. So the derivative of the natural log of x is just 1 over x, and on the bottom, limit as x tends to 0. 1 over 3x is really 1/3 times x to the power of minus 1. So differentiating that, we're going to have 1/3 minus x minus 2, or 1/3 x squared. 1/3 over x. So writing that here, we have minus 1/3 over x squared. This is nothing more than the limit as x tends to 0 from the positive side. Now, 1 over x over minus 1/3 x squared, we just use a reciprocal. We can multiply, the bottom goes here, and then this multiplies here. So we have minus 3x squared all over x. And this is minus 3x. So the limit as x tends to 0 of minus 3x will be 0. Now recall, we let limit as x tends to 0 from positive natural log of y equals limit as x tends to 0 of 3x ln of x. And we found that to be 0, which implies that the limit as x tends to 0 from the positive of ln of y equals 0, or as x tends to 0, natural log of y equals 0, which implies that y equals x to the 3x tends to 1 as the limit as x tends to 0. That is to say, the limit as x tends to 0 of the natural log of y equals 0 implies the limit as x tends to 0 from the plus of x to the 3x equals 1. Because if we were to take the natural log of 1, that's 0, and the natural log of y is 0, so both these equations are satisfied. So the answer is 1. Let us look at our sixth case now, where we have infinity to the power of 0, and consider the example: the limit as x tends to infinity of x 1 over x. And we can clearly see as limit x tends to infinity, this is going to go to infinity, and this part, 1 over x, will go to 0. So we're going to have an infinity to the power of 0. Now consider, let y equals x to the power of 1 over x. Therefore, the natural log of y is going to be 1 over x multiplied by the natural log of x. And the limit as x tends to infinity of the natural log of y equals limit as x tends to infinity of natural log of x over x. Now, as x tends to infinity, this will go to infinity, and this will go to infinity. So we have an infinity over infinity case. Let's use L'Hopital's. So we take limit as x tends to infinity, ln of x over x equals limit as x tends to infinity d dx of ln of x all over limit as x tends to infinity d dx of x. So that's limit as x tends to infinity. The derivative ln of x is just 1 over x. And on the bottom we have the derivative of x is just 1. So on the top, as x tends to infinity, this will go to 0. And on the bottom is just 1. So we're going to be left with 0. In other words, so we have the limit as x tends to infinity, ln of y tends to 0. This implies that the limit as x tends to infinity y, which equals x to the power of 1 over x, tends to 1. So our answer is 1. Let us consider the last case where we have 1 to the power of infinity. To do this, and we've already done it, but just to be clear, we need to know that the derivative of the natural log of x is 1 over x. And then the derivative of 1 over x is the derivative of x to the power of minus 1, which is minus 1x minus 2, which is minus 1 over x squared. So we need to understand these derivatives in order to do these questions. So continuing, let us consider the limit as x tends to infinity of 1 plus 1 over x to the power of x. And applying the limit, we notice that as x tends to infinity, this will go to 0, and this will go to infinity. So we have a 1 to the infinity case. Now, let y equal 1 plus 1 over x to the power of x. And we take the natural log of both sides, we get the natural log of y equals x times the natural log of 1 plus 1 over x. Rewriting this, we can say this is just the natural log of 1 plus 1 over x divided by 1 over x. Now if we apply our limit as x tends to infinity of natural log of y, we get limit as x tends to infinity of the natural log of 1 plus 1 over x divided by the limit as x tends to infinity of 1 over x. And then we find that we get on the top, as the limit as x tends to infinity, this will go to 0, so natural log of 1 becomes a 0. And on the bottom, as x tends to infinity, this becomes 0, so we get a 0 over 0, an indeterminate form. And then we can use L'Hopital's rule because we have a 0 over 0. So let us do that. So again, we have the limit as x tends to infinity of the natural log of y equals the limit as x tends to infinity of the natural log of 1 plus 1 over x divided by the limit as x tends to infinity of 1 over x. Well, this is just the limit as x tends to infinity d dx of the natural log of 1 plus 1 over x all over the limit as x tends to infinity d dx of 1 over x. So this is the limit as x tends to infinity. Working on the top, the derivative of the natural log of 1 plus 1 over x is 1 over 1 plus 1 over x multiplied by the derivative of this thing, 1 plus 1 over x. The derivative of 1 is 0, so we just need the derivative of 1 over x squared, and we said that's minus 1 over x squared. And on the bottom we have limit as x tends to infinity. Again, the derivative of 1 over x is just minus 1 over x squared. Now we note that we have a minus 1 over x squared here and a minus 1 over x squared here, and these will cancel. So we're left with just the top, limit as x tends to infinity, 1 plus 1 plus 1 over x. Now as x tends to infinity, this will go to 0, and then we're just left with 1 over 1, which is just 1. In other words, this is telling us that the limit as x tends to infinity of the natural log of y is 1. We know from natural log rules that y is just e to the ln of y, since they're inverse operations, the exponential and natural logarithm functions. And we know that e limit as x tends to infinity natural log of y is e to the 1, using what we just proved here. So we can conclude that y is e, which equals the limit as x tends to infinity of 1 plus 1 over x to the x. 7 different indeterminate forms took their limits using L'Hopital's rule. We looked at various kinds of derivatives of exponential functions, of power functions, of trigonometric functions. There's a lot of information. I left a summary detailing the examples we covered and detailing a lot of the derivatives we took. And hope you enjoy everything. Please click like, subscribe, and comment below, and look forward to seeing you in my next lesson. Take care, have a great day, and as always, please stay safe.